All right, welcome back, folks. So in the previous video, we talked about how to find measures of position in a data set when the median was the best measure of center. When the mean is the best measure of center, we generally have symmetric data. And we can do different things with data that are symmetric and with things like means. And so we're going to talk briefly about how we do that here, but we're going to revisit a lot of this over the course, because this part of finding the position of data in a data set becomes extremely helpful when we are talking about calculating things like confidence intervals later. Okay, and so you'll see why this becomes so important. But for now, understand it much like we understood the position that we talked about in the previous video. Okay, we're just going to find that position relative to the other data just a slightly different way, because the data are going to be distributed in a particular way, right? If we know they're kind of symmetrically distributed, right? We know the mean is probably the best measure of center. Okay, well, then we can find places in the data set a slightly different way, and we can say other things about them. Okay? So a z-score is essentially a way to compare values to a data set, right? So if we're talking about something like the average height of people, right, and you ask someone their average height, you could then take their height, compare it to the population average, right, and determine a z-score, how different it is from the average, okay, or a way of measuring a difference from the average. A z-score just gives you the distance from whatever the mean value is, whatever that population mean value, in units of standard deviations. How many standard deviations above or below the mean? Okay, so a z-score of positive 1.5 tells you that a value is 1.5 standard deviations above the mean. A z-score of -1 means it's 1 standard deviation below the mean. Okay, so values that are less than the mean value should have z-scores that are negative. Values that are greater than the mean value should have z-scores that are positive. And that plus or minus tells you, the position relative to the mean. The value tells you how far away from the mean the particular value is. Okay, so for now, we're just going to talk about calculating z-scores. Let's say the average height for a male in the United States is about 70 inches, with a standard deviation of about 3 inches. Okay, to find the z-score for a male who's about 74 inches tall, okay, we're going to take our raw score, the value we're interested in, which is x, subtract our population mean and our population standard deviation, and then divide by the population standard deviation, and that gives us the z-score. Okay, so that just means that a person who's 74 inches tall is 1.33 standard deviations above the mean. Okay, so 1.33 times 3 will give you 4, right? 4 inches. 1.33 standard deviations above the mean. And now the good thing about z-scores is the position is the same regardless of whatever data values we're calculating. Okay, so we can do this for all sorts of different types of data, okay, and still say the same things about a data value that's positioned with a z-score of 1.33 or 1.33 standard deviations above the mean. If we wanted to find one for someone who is 65 inches tall, well, then we would do 65 minus 70. Right? This is the value that we're interested in, 65, minus the population mean divided by the standard deviation, and we would get a z-score of -1.67. And notice that the z-score here is greater in value, okay, and 5 inches less is greater in value than 4 inches more. And so that's what you're seeing in the numbers themselves. It's not exactly a uniform change or anything like that, but that will occur, right? So the mean length of 1-year-old flounder in millimeters is 128 with a standard deviation of 15. Okay, so we know this is our population mean, 128 millimeters, okay, with a standard deviation of 15. millimeters. And the mean length of 2-year-old flounder is 160, standard deviation of 27. Okay. Call that 2. If we catch a 1-year-old flounder that's 145 milliliters in length, what's the z-score? Okay. Well, a 1-year-old is the first one, right? So our z value is going to be 128. Oh, I'm sorry. It's going to be our raw value that we're interested in, right? So we caught a flounder that was 145 millimeters. Minus the population mean for a 1-year-old flounder was 128. Divided by the standard deviation is 15. 145 minus 128. 17 divided by 15. For a z-score of 1.13. 1.133, however you want. And so this just means that it's 1.13 standard deviations above the mean. Okay, that's what we mean by interpreting the z-score. It's giving us a position relative to the data. Now that can tell us something about, again, about percentages, but we're going to talk about that in just a second. If we catch a 2-year-old flounder who has a z-score of negative 0.4, okay, what does that z-score mean? Well, that z-score means that it is minus 0.4 standard deviations below the mean. Okay, so what we're going to do is we're going to take the mean. The mean for a 2-year-old flounder was 160. 160. Okay, and then we're going to take our z-score and multiply it times the standard deviation, in this case, 0.4 times 27 for a 2-year-old flounder. 10.8. And so 160 plus negative 10.8, right? Z times X. Oh, I'm sorry, Z times sigma. The formula is on the next slide, you guys. And that should give us 149.2 millimeters. Below the mean, a value that's less than 160, that's what we'd expect. And so that z-score is giving us a position relative to where the mean is, as opposed to just a position relative to the other data like we talked about in the last lesson or the last video. But if we want to calculate the raw score like you saw in that last example, we want to know the height of a male with a z-score of 1.85. Well, we just take z and multiply times the standard deviation, because it's just the number of standard deviations, and then add it to the mean. If we had negative 2.18, we would subtract it from the mean. It just winds up being subtracted, essentially. Remember, negative z-scores should have values that are less than the mean. Positive z-scores should have values that are greater than the mean. Right? And the reason why all of this matters, the reason why z-scores are done, and the reason why we use all of this is because of something that happens to data when it's somewhat symmetric. And this is what's known as the empirical rule. Okay, if we have data that are symmetrically distributed, okay, then most of our data is going to fall within one standard deviation of the mean. Okay, generally approximately 68% will fall within one standard deviation of the mean. 95% will fall within 2 standard deviations. And almost all of the data, 99.7%, will fall within 3 standard deviations. I made that line a little long. Here's 3 standard deviations. Okay, so this is z equals 3. Right? At 2 standard deviations would be, I've got these lines drawn a little strange. Z equals 2, and z equals 1. okay, -1, and so on. So the z-score gives us a position relative to the other data, but also tells us something about its position. Well, I'm sorry, it gives us a position relative to the mean, but it tells us something about its position relative to the other data. Right? So we could, and you will see this in upcoming weeks, we could talk about how much data is on this side of a particular value, or how much is on this side of a particular value. And we can be pretty accurate about it if the data are symmetrically distributed. Okay, and the empirical rule is just a way for talking about where we'd expect to find most data when the values are symmetrically distributed about the mean. And we're going to build off of this over time. And we're going to use this type of bell-shaped distribution, which I believe we've talked about in some of the previous lessons. And so, for example, let's say we have the height of a 73-inch man is 1.16 standard deviations above the mean height for men. Okay, the height of a 68-inch woman is 1.5 standard deviations above the mean height for women. Who's taller relative to their population? Okay. Well, if we just look at the values, right, or even if we just say, let's say the mean height for men is 70, and we could really calculate what the value is from here, but we don't have to do that. If we just look at the values, well, the man's taller, right? And if we knew the mean, we could figure out exactly, how much, and we could probably calculate again what we need to know the standard deviation to. But if we knew those values, we could probably calculate directly the mean. Okay? But we don't need that because we have the z-scores. A z-value of 1.16 is closer to the average than a z-value of 1.5. The person taller relative to their population is going to have a larger z-score. They're going to be higher up in this distribution. They're going to have more people below them, a higher percentile in the data, if you will, okay, because they're further away from the mean. And we know that immediately from the z-score. We don't need any other information. The person who's taller is going to be the woman who's 68 inches tall compared to the man who's 73 inches tall, because her score is further from the mean. It's further from the average. We will talk a lot more about z-scores, but in order to understand how they're helpful and how they're useful and what we use them for and all those types of different things, we first have to talk about probability, which will be coming next week after your first test. If you have any questions or if there's any other way that I can help you, please let me know.